So this time we are going to talk about medical imaging, and we are going to do that using the Fourier transform in its two-dimensional version. And in that case we are going to have, instead of time, we have coordinates x, y, and usually we will transform these into their frequency equivalents, and to distinguish it from omega for time, I will call these guys u and v. So if you have an image that is, say, an intensity that is given by pixels with coordinates x, y, then we can, of course, Fourier transform that in one dimension. And that would be, in this case, going this way. And now I have the transform, the Fourier transform, in the x direction. Note that in this case, I'm using not the omega, but the 2 pi f equivalent. So that's the reason you see this 2 pi factor appearing here. So now the next thing that I can do to create a two-dimensional version of this is say, okay, I'm going to take this component, and I'm going to now transform this in the y direction. Isn't it? And now I have basically, in sequence, I've done two Fourier transforms, one in the x direction, and then I took that result and transformed that into the y direction. And I can actually combine these two expressions. And I'm indicating here minus infinity to infinity, but they apply to both integrals. And this would give me the, I would say, Fourier transform of my image in spatial frequencies uv. And as your homework, I will give you the little exercise to do that with the inverse transform, and of course it works pretty much the same way there. So now let's start with a simple imaging problem or example, and that comes from optics. And most of you probably from high school or some other background that you may have, you know, you're familiar with ray optics. Say you have some object and you have a lens, and then you can basically make a picture, or you can make a video recording, or what have you. And there is actually a field that's called Fourier optics that uses the Fourier transform specifically. And as a matter of fact, maybe you never thought about it like that. At least I didn't before I looked at it the first time. But a lens is kind of a Fourier transformer. If this is a lens, and if this is, let's say, its focal distance, and I would have some kind of a screen here, and I have a point light source sitting at this optical axis at one focal distance, what will happen is that light beams will go this way, will go that way, and will go that way. And what you have here actually is some kind of a point source that we typically in the time domain indicate with a delta, and you can do that in the spatial domain as well, of course. And here you have a kind of continuous illumination of that screen. And that is similar to DC in an electrical signal. And just as I asked you to look at these pairs, just recall that if you have the Fourier transform of a delta function in the time domain, then you basically get a constant. So in that sense, the lens is doing exactly that. It transforms a point source into a continuous illumination. And to that extent, it is a lens is kind of a Fourier transformer. And you can take advantage of that. And one kind of common example is something I'm showing in figure 7.8. And that's called the 4F system. And that system deals with, let's say, that all the f's that we use, all the focal distances are equal here. We have 4 f distances here. We have actually at this point, we have a lens. And at this point, we have a lens. At this point, we have a screen. And at this point, we have some kind of an object. And what you now have is, if you go here, and this is the focal point there, you basically get something that looks like this. And this is going directly through that focal point of both lenses. So now this thing is called the Fourier plane. And what's interesting is that in this 4F system, and there's basically nowadays almost all optical systems have this 4F approach. Microscopes use it, but all kind of imaging systems use this actually because it has an enormous amount of advantages. One of the funny things or fun things you can do with it is, of course, if you have an image, you get actually the Fourier transform of that image here in this plane. And then basically you do again a Fourier transform. And since the duality principle indicates that the Fourier transform is very similar to the inverse Fourier transform, that's something that came up also last time when we looked at the mathematics of it. Due to that duality property, you actually get the inverse image of the object at this point. That's, by the way, another homework assignment that I gave you to show that. So that's nice, but it also means that I have the Fourier transform of my image available here. And since I have that available here, I can do all kinds of manipulations in the frequency domain of my image in an optical fashion. I don't need to do that in a digital way. I can actually directly in an optical, in the optical plane do all these things. And so, for instance, I could remove the center of my image here in the Fourier plane. Do you have any idea what effect that would have on the image here? If I just, oh, you know what, I'm going to kind of block this here.
So you can lead up the low frequency component so you can image with the shutter.
Yes, yes. Yeah, you basically, since this is the center, you would remove low frequencies. So you would basically, relatively speaking, you would enhance the edges. Just like in a power spectrum where you're close to zero, you have the low frequencies. That's here in this image is the same way, that close to the center you have the low spatial frequencies. If you remove them, the high spatial frequencies survive, and they basically represent the edges. So you can do a lot of fun stuff. And I actually have an exam question about this too. You can have some fun with that. So now we are going to move on to the main topic of of this lecture, and that's applying the 2D transform in medical imaging. And we're going to get started with CT, computer tomography. And let's say that we have an object that we want to scan, and that object is situated in this circle with radius r. So our object is situated there. And the only area where there is, in this case, an effect on the CT data collection is within the object. So we assume that outside the object, let's say your head is in this circle or something like that, or a body part, that outside that body part there's basically air and there is no absorption of X-rays. Then we are going to move a source and a detector. Let's say that this is the detector and this is kind of the X-ray source. We're going to move that that line, that source detector line, in this direction. And since if we move this thing in an more or less, not more or less, in exactly a constant speed, then basically this the size of this vector is given by time. If v is constant, then that length of the vector is going to be given by time. So I'm going to basically use that and denote that vector as t. And the angle in this case between t and the, let's call this x and y, between the x-axis is called theta. And then the next time I'm going to change theta again, and again I'm going to move that thing over my object, and that object is somewhere in here, this radius. And then I move my theta again, and I move that line of response, it's called, again over my object within this circle of radius r. Now every time that I do that, I get a absorption. Let's kind of say this is indeed a CT scan, so it's an X-ray signal, and it's a detector that detects the absorption. Every time that I do that, I basically compute the effects that I can represent here by all the little pixels that are lying on the line of response on the LOR. And so this piece and all the pieces that are on this line of response are going to add to the signal that I'm going to find in my detector. This thing I'm going to call just in polar coordinates. Instead of calling it r or xy, I'm going to call it r. And I'm going to call this thing phi. And yeah, if I kind of indicated this little area as an area, I would call it dx dy, isn't it? But in this case, since I'm using polar coordinates, I'm going to express this in polar coordinates, which means that it's going to be r dr d phi. And because this area is roughly r dr, and this piece is d phi. And you can see here, and that's something we're going to use a couple of times, that t is basically r times the cosine of the difference between the two angles phi and theta. And this, by the way, is figure 7.9 in your handout. So it's clear what we are doing. We're moving this line over our object, and we are measuring in our detector what's going on. So now we are going to say what we are interested in is what this detector is measuring. And let's say that the contribution of absorption in each of these little green elements is A of absorption R phi. And if I wanted to have the contribution of my whole object, I would just integrate that over R and phi. I would use this to integrate it, and I would have the absorption of the whole object. But that's not what the detector is measuring. The detector is measuring only the stuff that's on the line of response. So how do we do that? Well, we have something for that. And I'm writing it on purpose a little wide, but you can ignore that. Because I'm going to write something in between it in a little bit. I'm going to use the sifting property of the delta function here to pick all the points on the line here. And how do I do that? Well, I can actually use this equation here. Because for a given t and theta, this is going to pick out all the points for r and phi for which this thing evaluates to 0. And that means that then, by simply integrating it, I can apply the sifting property. And so if I apply the sifting property here by this integral, then I'm just picking out exactly the points that I need. And this function I'm going to call mt theta. And as a matter of fact, in image processing, this is also known as the radon transform. And there is even a command in a function in MATLAB, the function radon and iRadon, to do radon transforms and inverse radon transforms. So this basically and if I leave this delta function out, I just get the complete absorption of the whole object. So guess what I'm going to do now? It's not so difficult to guess because we're talking about Fourier transforms. I'm going to Fourier transform this thing. And as a matter of fact, I'm going to leave theta for what it is. I'm going to Fourier transform the t domain. And in order to do that, I basically could apply that to the whole thing. But since t is only here, I can also say, well, I'm going to, in principle, just add it at this here. I should have given myself even more space than I did. But as you can see, I'm just applying here the Fourier transform. And now this thing will become mz theta. What is mz theta? How do we evaluate integrals with the delta function? Mark? Yeah, you just plug it in and you use the sifting. So we can do that here. And for t, we are just going to plug in this value. That's kind of what we are going to find. So now we are going to come to the magic of the CT algorithm. Just let's keep this thing in mind. And let's do the following. Let's kind of determine what the 2D FT transform of A R phi is going to be. Or, if you want to say it, AXY. I mean, you can do AR phi or AXY. It depends on whether you use Cartesian or polar coordinates. It doesn't really matter. So let's start with the simple one, because that's an equation we already know yet. That is that, let's say that the Fourier transform of A is going to be this. That's just a standard Fourier transform. In a 2D version. And see, we have x, y. We're going to go to spatial frequency coordinates uv, just as we did at the beginning of the lecture. And then this is the expression that we figured out for the 2D Fourier transform. Well, since we are playing here with polar coordinates, it's actually practical to transform this also in polar coordinates. So in this case, we're going to put uv in z and theta, and we're going to put xy in r and phi. So if we use that, and you can look in the handout to follow all the steps that you need to do to get to this point. If you do that, you get the following expression. And again, instead of going from minus infinity to infinity, since I'm in polar coordinates, I can say, well, everything outside R is 0 anyway, so I'm not going to bother about that. Hence the R here. My absorption function, of course, now is in polar coordinates. And then if you do a little algebra, you will see that the exponential evaluates to this. So this is my 2D transform of my absorption function. written in polar coordinates. Is there anything you notice here? They're the same, yeah. Isn't that great? They're the same. This is called the Fourier slice theorem. So if you measure the radon transform with the source detector setup, and you do the 1D Fourier transform, then actually you get the same thing, because this is a 1D Fourier transform. You get the same thing as when you do a 2D Fourier transform of the absorption function. That's fantastic, because that means that the 2D inverse Fourier transform of mz theta will give you AR phi, i.e. the image. So it's not like, oh, it is CT stuff. We are just guessing a little bit what that image would be. No, the math basically tells you that if you do this measurement, you do a 1D Fourier transform, you then do an inverse 2D Fourier transform, then basically you get exactly your image. Of course, in reality there is noise. In reality, this line has some thickness, and so does this area. So it's not all that fantastic as it is on paper or on the blackboard. But in principle, it is an exact reconstruction. If you start up MATLAB and you do, we'll do that, we do program 7_2, you can see some of that stuff happening. Let's kind of do that. The programs, etc., and the handouts are all on chalk, in case you hadn't seen that yet. So you get, initially you get three figures. One is the Shep-Logan phantom. That's kind of a standard test signal that people use in image analysis. And that is available in MATLAB, so I didn't make that up. That's kind of available in MATLAB to be used. Then the next figure, figure 2 here, is the radon transform of this Shep-Logan thing. So that's basically this function, the absorption function that you see here. As a matter of fact, they are usually a bit sinusoidal in character. It's actually also an exam question that you kind of look at the radon transform of a unit impulse, and you will see that you get sinusoidal-like signals out of that. And then finally, in the third picture, you see what happens if we apply the logic as we just explored and reconstruct our image. And you can see it's not as good as the original, but it's pretty good. And it's actually already with a certain finite step size. If you now hit the return button, you can see how the figure still is kind of okay if I go at a lower resolution, but now you start to see ugly artifacts. And of course, the coarser my resolution is, and every time you hit return, you can see that happening. The coarser that resolution is, the poorer the result. And you get more and more artifacts. And so in this program we use the standard radon and iRadon functions in MATLAB. And for your homework and also in your exam questions, you're allowed to do that. I'm not expecting you to write your own radon and iRadon function. No need to do that. So this is the way that CT is still using, this is the algorithm that's still being used often in CT. Of course, nowadays there is also a lot of medical imaging occurring with MRI. And that's the other part that I want to talk a little bit about. The MRI signal itself and where it's coming from and how that can lead to an imaging result. Let's first talk a little bit about the signal itself, the NMR signal. In case of the CT, we have an X-ray signal. It goes through your object, and then your object basically absorbs some of that radiation, and then whatever is left is what you are measuring. That's relatively simple to understand. The NMR signal, nuclear magnetic resonance signal, is a little bit harder to understand. And to be honest with you, the real way to thoroughly understand the NMR signal is through quantum mechanics. And that's a bit much here to give a mini course in quantum mechanics. Even if I could do that, it would take lots of time. And so there are a lot of explanations available in textbooks and also in online videos where people give you popular explanations of that. And I want to kind of give you a little warning here that a lot of these explanations, although they work well and they make you think that you understand it, they're actually simplified. And in some cases, they are even simplified to the level that they're even incorrect. So you have to be a little bit careful. So what happens if you look at it from a macroscopic physics perspective? Because again, I'm not going to go into the quantum mechanics here and the Schrödinger equation and what have you. The idea is the following, that if you have a strong magnetic field that we are going to indicate as B0 or B0 in the Z direction, then what the nuclei, in this case the nuclei of hydrogen, so the protons, are doing is they are basically spinning. And because they are spinning, they create a magnetic field. And this spin, just as a toy spin, is also wobbling a little bit. So it's like, you probably have seen that when you played with a spin toy when you were younger. Or did you guys not play with spin toys? You did? Good. So then you have seen these movements, and that's called precession. And that precession occurs at a frequency that's called the Larmor frequency. And it's pretty simple. The Lamar's frequency is a constant at, in our conditions, it's 42.6 times the magnitude of your magnetic field in Tesla. And that will give you the Lamar frequency in megahertz, so in millions of hertz. Now, if you bring in this strong magnetic field in an object, then these, I would say, vectors start to align. And most of them will start aligning in the low frequency or in the low energy state, which means kind of going along with the magnetic field. But a small minority will actually not do that. They will kind of go into the high energy state, and they're actually just opposite of this strong magnetic field, B0. And the other thing that's kind of interesting to know is that when you hit this thing at exactly the Lamar frequency, you get a resonance effect. And that resonance effect causes some of these spins to flip. And the way that you can more or less visualize that is that when you have, let's say, an X, Y, Z axis, then you could say that when you have your standard magnetic field here, you will have an kind of a net vector that's pointing in the Z direction, and we will call magnetization Z. And now when I hit this, this tissue with a radio frequency exactly at the Lamar frequency, and I do the right amount of energy, then I can flip this angle in the XY plane, and I get an XY component. And because this is basically exactly a 90-degree flip angle, this thing is also called a 90-degree RF pulse. And again, this is called the flip angle. And so what you see is that you get basically a net effect of magnetization going from the Z direction into the XY direction. And that's important. Why is that important? It's important because this component you cannot measure. It is so small relative to this strong magnetic field that you cannot measure it. But this one is perpendicular to that strong magnetic field, and that's the guy you can measure. Now this process is called the excitation, caused by the RF pulse. What you now get if you stop doing this, stop emitting this pulse after the pulse is turned off, is that you get relaxation. So this thing is actually going to relax back to the original state, which is kind of logical. But the way it does that is as follows. It actually does not simply go back, but it basically turns like this. And that is because these things all of a sudden are in phase when they flip. And during the process of relaxation, they go out of phase again, which means that the XY component is decreasing. But and you can see that I didn't draw it very correctly, but you can see that the radius of this spiral is decreasing. And while this is happening, the MZ component is restored. And so you have that the XY component that initially is there basically relaxes back to the MZ component that you originally had. And while it's doing that, because of the fact that all these units start to dephase, first they have all the same phase and then they start to lose that phase, the XY component is decreasing. So the way that you usually see that in time is that, well, if your pulse is here, your RF pulse is here, then basically what you will see is that this is kind of the envelope I'm drawing. This is what your signal is doing, and this is you see because of the XY deterioration caused by the dephasing. The dephasing, so the reduction in XY component, is called T2 relaxation. And the restoring of the Z component is the T1 relaxation. So T1 is the restore of MZ. T2 is the decrease in XY. And again, this is a macroscopic model of what's going on, what's really going on. You can only understand if you go into the details of the quantum mechanics. But this is a pretty accurate physical model for the purpose, for our purpose that we are using. So now let's kind of think about, we put our hat of an engineer on, and let's make an MRI system. We know how it works now. We have we go to, what is it, Walmart, and buy this huge magnet. And we go to Radio Shack, who's, I think, going out of business, or maybe already out of business, and get a very cheap radio frequency emitter. And we're going to build our MRI system. So what's the problem that we immediately have? Well, we can do this. We can sit in this strong magnetic field, and then we can give this body a kick with this RF frequency, and then we can measure what signal is coming back. The problem that we have is that that signal is coming from everywhere in our body. And so the only thing we can do at this point with our system is detect whether there is somebody in the field or not. But that's not very appealing, of course, because we can just look and then we know that as well. So the idea is that we want to be able to get spatial information. So how do we do that? Well, we do that by encoding the X, Y, and Z. And one of the things you can do, for instance, if you put somebody, this person is really sick, as you can see, it's very anorectic. What we do is we have this person lying down in this huge magnetic field. And as I said, if we now give a radio pulse, we will, at the right Lamore frequency, then we will excite the whole body, and the signal we get back is going to be from the whole body. So what are we going to do? We are going to make a slight modification in B0 by creating an additional field we indicate by GZ. So we call this the Z direction. The direction of B0 is in the Z direction. And now this actually works because now, since the Larmor frequency depends on the magnetic field, which is in this case B0 plus whatever I'm doing to modify it, the Larmor frequency is going to be different in every slice of the body. And if I now give a radio pulse exactly compatible with this frequency, I'm going to get this slice. And so now I know that if I turn in some RF frequency into this subject, and I know because I can calculate that this is the area that I'm interested in, then at least I know it's not from the whole body, but it's coming from this slice. It's not great, but it's better than nothing. Yes?
This might be a stupid question, but like...
So the next thing that we need to do is to see, now we know that it is coming from the slice, is can we do something also, if this is the slice, and this is the Y direction, and this is the X direction, can we do something to encode that? And the answer is absolutely. First of all, what we do, and for instance, let's do that in the Y direction, although I could also turn that around. But let's do that in the Y direction. I turn on a magnetic field that I call the GPE. And I turn that on very briefly. What's going to happen? The guys that are now rotating at the Larmor frequency are going to rotate at a little bit different speeds. These guys, if the field is going in this direction, these guys are rotating a little bit faster, these guys are rotating a little bit slower relative to the other ones. And I do this only briefly, and then I let it go again, which means that at that point the Larmor frequency is going to go back to what it was. But because these guys were running a little bit harder than these guys, there is a phase difference, and that phase difference is going to persist. So this gives you a phase difference. And then the next time, and at that point I'm going to do the measurement, I bring in another field, the GRO, and that is going to create a slight frequency difference. And yeah, basically now I'm pretty much where I want to be, because I can now, by turning this thing on, select my slice. I basically do this and I hit the units and at a Larmor frequency, and then I get a signal. Then I basically do this for a brief time, and I get a phase difference. And then I turn on that one, and I get a frequency difference. So now I have coded basically the whole thing. And I'm going to show you how that is done in practice. That's one of the figures that you have in your handout. And this is a very basic way of doing an MRI sequence. There are much more sophisticated sequences available. But this is the basic idea. You turn on your gradient in the Z direction, and you come in with your radio pulse. Then you turn on your phase difference, and you do that actually a couple of times, and you will see in a minute why that is important, that you do that a couple of times. And that creates a phase difference in the Y direction. And then finally you turn on the X field, and during that time you are actually measuring. And if you measure at this point, you know three things. You know from what slice in the Z direction it's coming. You know that there is a phase difference in the Y direction. and you know that there's a frequency difference in the x direction. And so now you have coded x, y, and z in your signal. And again, this is a very basic pulse sequence. Let's call it pulse sequence. It's the most basic one that you often see depicted in MRI textbooks. But it's nonetheless drives the point home what we're doing. And you can change and you can make changes. And for instance, in the textbook or in the handout, I'm talking also about the echo, which is being used often. But the principle is basically still the same. The only thing that other more sophisticated sequences do is kind of deal with the fact that your measurement here is taking place when most of your signal is already gone. And so there are all kind of tricks to kind of deal with that and get a larger yield of your signal, which of course translates in a better signal to noise in your image. So now let's see how we use the Fourier transform to translate this procedure into an image. So let's say that in a voxel, and a voxel is basically a three-dimensional version of the pixel. A voxel in the body gives a signal that I call x, y, and t. So it's a signal. You just saw a signal, and I mentioned that the signal was a function of x and y, and of course it also varies over t. That is basically nothing else than an oscillation. You saw that. And that oscillation I could write as some intrinsic intensity function that is associated with x and y. And now we are going to present, and that's probably something you may not have seen a lot, but we are going to present the oscillation as a complex exponential. Right? Think about the Euler formula, where you have cosines and sines basically being components of the complex exponential. Now we are actually, instead of using cosines and sines here, we are expressing our oscillation that we just saw as a complex exponential. And think about Euler. Huh? You forgot about that. So how is this working? Well, this is already starting from the idea that we know that it's coming from the slice. But we said that the frequency was encoding the x direction. So here is the fx. And that the phase was coding the y direction, hence the phi I, y. And I kind of showed you in the picture that we do the application of the phase a couple of times. And so let's kind of put that also in the and let's call that tau, because we do that as a different time scale. In that case, we can now say that S, X, Y, T is that intensity function times J 2 pi fxt plus phi y tau. That's how I encoded my oscillation. Right? So what do I need to do in order to represent my measurement? Over time, over the two time scales, t and tau. Well, at a given t and tau, my measurement is going to consist of the contribution of all the x's and all the y's, isn't it, in the voxel. So I'm going to have to integrate over x and y. And there we go. That's our measurement. So where the radon transform was the measurement in the CT scan, this is kind of your measurement in the MRI recording. And as a matter of fact, there is nothing against if you would change your routine of moving detectors, etc., to use the other approach for MRI, but this is currently more commonly used. This thing, by the way, is in MRI term represents the so-called K-space. So now let's do some simplification again. Since we know that fx is nothing else than something that's proportional to the magnetic field that we apply in the x direction. So I could say that's some constant a times x. Same thing here. I know that is some constant in that direction. If I then simplify the notation a little bit further, and I call this u and this v, then I can also simplify or change this in u and v, and then it will become this. It may be a bit difficult with all this white and green on the blackboard, but look carefully at this equation. What is this? The inverse Fourier transform of your image. Yeah. So that means what I can conclude from this is that that I can reconstruct my image by a 2D Fourier transform of my K-space, mt tau. So here you see the third example where we use the Fourier formalism, the 2D Fourier formalism, in imaging in a very effective way. I implemented an example of such a reconstruction in a MATLAB routine. That's program 7_4. So let's run that thing and let's see what that gives us. So if you compare this with figure 715, then you see that I started with an image where there are 2 pixels. And I then basically show you here for a number of different phase implementations. Here it's one direction, here no, and here in the other direction. And here we have the frequency encoding. And then you can see that this program will then show you what the case space looks like of this image. And it will also then show you what happens if you Fourier transform that. And you can see that indeed you find in the intensity reconstructed intensity image, you find your 2 pixels. That's also part of one of the exam questions, because that same question that I'm going to ask about the CT, what happens if you have a radon transform of a delta function, is also what happens if you have a case space and a reconstruction of a delta function. That basically concludes the part. So the only thing that I need to do is give you the homework, and I forgot to make a note, so I will send that to you, Graham, and then maybe you can post it on Chalk for this lecture. Are there any questions before we stop? We did quite a bit. We did kind of Fourier optics and CT and MRI in a single lecture, but as you can see, the common denominator is the 2D Fourier transform. So, and the only thing that's a bit complicated may be the algebra going from polar coordinates to Cartesian coordinates. But for the rest, once you understood the Fourier transform, it's not that complicated. Okay, then we're done.